Hey everybody, let's do the part 2 on the chapter 3 pretest. Now in the first one, it always mesmerizes me, intrigues me, a better word, how when you put one of the tensions to the side, like we have right here, when this tension is put to the side, it throws people off. The nice thing about that tension is it ain't a problem child. So if we bring in our, all right, so there is our, here is our, come on, let's go. I want it, come on, just grab it already. Here we go. All right, so if we bring those in there, you'll see, oh, all right, if I bring this in, we only have one problem child because the FG, that weight there is pulling straight down, so there's our W pulling that way. So all we have is this T1, that is a problem child. T2, this is not a problem, so we only have one problem child that needs to be broken down into X and Y components. It's that simple. So it says, on the diagram below, draw and label the forces acting on the ball. So in black, keep this in black. All right. So pulling down, they said put it in terms of W, so we're going to call it W. So there is W, lowercase w for weight. Then we have T2 going to the right. Some string there tied to the right, T2. And then we have T1 going off at some angle there. Now notice we gave an angle to the normal, to the horizontal there. So we put theta right here. Okay, now, sometimes they'll say, do not draw components. I'm going to redraw it. All right, draw and label the forces. They'll say, draw and label the forces, and they'll put not components in parentheses. So we'll draw it over here. We'll draw the components. So T2 is no problem. W, so no problem. T1, which I didn't label, by the way, it's T1. T1, there is our problem. I know I just drew it at a different angle. All right, so T1's our problem, so we need to break it down into X components, and then our Y component. I didn't draw it to scale, of course, because you're going to see something in a second. So I'll probably make it longer just to, let's see, so first of all, change the angle to get this right. All right, so that's good. So to get this right, we need T2 and the X component of T1 have to be identical, right? So let's see how that worked out. Does that look good? Not bad. Yeah, good eye, Gruber, good eye. So T1X has to be identical to T2. T2 we do nothing with. T2 is just an X direction. That's it. We do nothing. And so I got to make this longer. That looks about right. I'll fix it in a second. Now the vertical component here. So there's T1Y. We need a little micro eraser so I can erase the length of this. Okay, beautiful. See, that's why I could use color. This looks so nice. So that's T1. T2 goes that way. Now remember something we just said T1X has to be the same length as T2 because we have equilibrium. Well, that also means that T1Y must be the same length as W. Those are the two forces balancing each other in the Y direction. So all I'm going to do here to make it look better is make my work longer. So I'll do it like this. Grab that. Yeah, look at that. That's nice. Look at that. There you go. There is now that is a beautiful equilibrium problem drawn relatively to scale. Okay? So this is actually a 3-pointer here, just to let you know. This would be 3 points. right? Because you had to draw 3 vectors, right? If you leave out 1 or 2, they would only give you 1 or 2 points, so you have to be ready for that. So we have, let me just get rid of all those, these things. No. Hello. Get rid of this. I'll put a little pile of, there we go. All right. So derive an equation for tension in terms of T1. Now, of course, you see that this is forces, so this is not a VDAT situation. This is an FBD. So let's FBD it, which we already did. We should, actually, it's over here. Right, they're already setting you up. Label the forces. There's your FBD. So A is your FBD. FBD. So now that you got the FBD, now we need our X and Y sigma equations. Let's derive sigma Fx and sigma Fy equations. All right? We have an equilibrium situation. It's suspended. We have equilibrium, which is a beautiful thing when we're in equilibrium. Sigma F, I'll put Y next to it. So sigma Fy equals 0. If you like putting 0 first, you can put it. That's going to equal T1Y. I declare T1 is positive, and the W will make negative. So it's going to be T1Y minus W, because W is down. That, of course, equals 0. So that tells us, since the sum of those forces is 0, and it's one vertical force minus one upward force minus a downward force, right? Or added to the negative of the downward force, which is the same as minus. Again, I'll show you later. Just trust me for now. We now get, so T1Y equals W. Okay. Now, notice we want to derive an equation for tension 1 in terms of W and theta. Okay, so we want in terms of tension 1. So let's see, T1Y, was that say T1? Yeah. T1, T2, cool. Okay, T1Y equals W. So let's plug in. What does T1Y equal? Well, since this is theta here, that's the opposite side. That's your sine theta function. So we have W equals T1 sine theta. W equals T1 sine theta. So that's done. That's why I'm like, was this supposed to be T2? That's it. Notice, we're done. Well, no, we're not done yet. We're not done, because we're solving for T1 tension, T1 in terms of W and theta. So it's going to get rid of these little extraneous little marks. All right, so to get it in terms of W and theta, we have T1 equals W over sine theta. That's it. So that's it. Now, why do I remember being T2? Did I? Hold on, because that's fairly easy. T1. Yeah, all right. Yeah, we didn't even need the X direction to get this, all right? Simple enough, all right? So, okay. So, don't mind me. That's right. That's as simple as it was. I'm just checking, because I thought I changed it. Maybe I didn't. Hold on. Now, the answer is not here. 3, that's 4. Interesting. Oh, there it is, right there. No, I see. I kept this simple. That was a real simple one. That's a piece of cake, all right? That's easy. That's easy enough. So we got T1 in terms of W. We're done. My apologies. I was thinking of the problem that's coming up in a little bit. So I'm going to go skip to that one right now, which is number 7. So let's take a look at number 7. So it says we got a horizontal. So notice this is an identical problem here, right? It's the same exact picture. We have a horizontal arc to the right, and the figure above will break when the tension exceeds the value T max, right? What is the maximum mass M that the hanging object can have without the horizontal wire breaking? Assume the wire on the left does not break prior to the horizontal wire breaking. Okay. Must be in terms of T max, theta, and any physical constants. All right. So now what you got to realize, we have that T, there's still a force up here that we have to consider. Right? There's a force pulling up here. So I'm going to call this T max. What's interesting, you're like, well, what does this mean, T max? Well, we just want the maximum force we can have without it breaking. So let's just call it T max. Because if it says, it says assume the wire on the left does not break. All right, so it's in equilibrium. So it's just before breakage, right? Just before, right? Breakage. So it's still in equilibrium. Don't let those things confuse you. If they say it's going to break, well, it didn't break yet. It's just the point of breakage. So that makes it simple. So what do you want to call the other one? We have that M pulling down, and let's call this T2 for now, right? Let's call it T2, since that's T max, right? Now, notice, we want the maximum M. So we want M equals, boom. And it has to be in terms of T max, theta, and any physical constants. So notice what it can't be in terms of. Cannot be in terms of that T2 that we just named. Ah, dang it. Okay, no big deal. Well, is this a VDATN problem? No, this is an FBDN problem. So we're going to FBD it. All right, so we have T max. So notice identical to the last one. Identical. We have T max pulling this way, which is like our T2 from before. So you know what? Let's not call it T2 because it's going to be identical to the last one. So let's just go and change that. Let's call it T1. Sorry, guys. We'll call that T1. We'll call this T1. This way, it's the same thing we just did. And there's no difference. All right? So we got T max. We got T1. We got not M pulling down, but we have MG. It's capital M, by the way, capital M, G. And then, of course, we have our vertical component. And then we have a horizontal component. I didn't draw them to scale, just save a little bit of time. Okay, so we have T1X here, T1X, and then we have T1Y, T1Y pulling up. And you know from your first step, of course, which is your FBD in it, your second step will be to get your sigma F equations in the X and your sigma Fy equations. We know it's 0 for both because it says just before breaking, they both have a sigma F of 0. It's an equilibrium, right? So there's no net force. Okay, so for the X direction, we're going to have, I'm not supposed to be doing this in red and pink. So let's do it in red. Dang it. All right, let's do the sigma Fx in red. Got to remember my colors. And watch, we're going to have that eerie thing where the purple is going to come back through. Interesting, watch. So sigma Fx equals 0, which equals T max to the right minus T1x to the left. Okay? And for the other one, we have in blue, we got sigma Fy equals 0, which equals T1y up minus mg down. There you go. Okay. So we need mass in terms of T max. Okay, so if we did that, you'll see, oh, we take this. This one sets us up for mg equals T1y. T1y equals T1 sine theta, right? Because theta is here. Check that color. Okay, theta is here. T1y is opposite that, so it's going to be the sine function. So mg, as we said, equals T1y, or mg equals T1 sine theta. Okay, now we have m in terms of a physical constant, theta, as it was requested, but we have T1 in there. We got to get rid of T1. So how do we get rid of T1? Cannot be here. All right, cannot be here. So what do? Look in the other equation. Check that out. Let's see. On the equation. We got T max minus T1x. Well, go to red. These things are equal to each other because they both add up to 0. T max equals T1x. I noticed something. That's it. T1x is T max. And T1x is going to be T1 cosine theta. So what we do is, let's solve for T1. And we get T1 equals T max over cosine theta. Take that and shove it right in there in T1. And we get a final answer, which we'll deal with in the dark purple there. We'll come down here. Numbering this, by the way. So this was number 2. This was 2 right here. We did 2 there. We did 3. All right. So FBD, number 1, and then over here. All right, yeah. Let me go back to my numbers. We did write them in an order, so let's just leave it that way. Let me get rid. What the heck does that say? No. All right. Make this 2 as it said. So 1, 2. That's 2. This was 3. Then here's 4. All right. So 4 is going to be subbing for T1, and we're going to get mg equals T max sine theta over cosine theta equals that. I'll put the final answer here. That's going to be m equals T max. Hey, remember something. Sine over cosine is tan of theta. Tan theta over g. There you go. So that shows us, right? The maximum mass you can have is a function of T max, right? The maximum mass you can have is a function of whatever the maximum is. So notice something. If it's not a very strong spring, that means T max will go down, which means the mass goes down, right? It's also a function of theta. So as theta goes from 0 to 90, we know tan of 0 is going to be 0, and then tan of 45 is going to, right, is it? Yeah, tan is opposite. There's no opposite side of an angle of 0, right? Because that would mean T1 is on the ground. There's no opposite side. So tan of 0 is 0, right? Right, because the sine of 0 is 0 and the cosine of 0 is 1. Perfect. Okay, so, and then it goes to 1 and it goes up to infinity. So tan goes up as theta goes up, right? So that means the mass would go up also, right? Mass would go up. Oh, and what's interesting, it says, assume the wire on the left does not break prior to the horizontal wire breaking. What that means is, if you go up to, if you assume the wire doesn't break, that means as theta approaches 90, tan of theta approaches infinity. I want to make a little note here, right? See, never thought of that problem in terms of this. It's pretty cool. Make a note. As theta approaches 90, tan theta approaches infinity. What this means is, since it said the wire will not break, the wire on the left does not break, so tan approaches infinity, so mass that can be held approaches infinity. Sick, right? Because it says assume the other spring T1 doesn't break. So that also approaches infinity. So that's an unbreakable string. That is cool. Okay, so I think that's all the problems in, yes, that's all the problems in whatchamacallit? In FBDs. So I figured I'd derive them for you. Even though the answers are there, I figured I'd derive them for you to let you see how they work. All right?